Hello, this is eDoc2020, and today on the bench we have this composite video splitter, which is Radio Shack catalog number 15-1103, rated 1987, and today we'll be disassembling this and reverse engineering it to see how it ticks. Welcome to the video. This is the inside of the video splitter, and I need to offer a correction. This was actually made in 1996 to 1997, not 1987. So here's the top of the circuit board. If you'd like to have a go at reverse engineering this yourself, you can take a snapshot of the video here. And now, this is the bottom of the circuit board with all the solder traces. I don't think there's anything interesting under the capacitors. So if you'd like to have a go at reverse engineering this yourself, you can also take a snapshot of the rear here. And now I will try to reverse engineer the schematic of this myself. One moment, please. The reverse engineering is complete. But before delving into the schematics, I suppose I should demonstrate what the video signals look like and why you need actual electronics in order to split a video signal. Okay. This is what a video signal looks like on the oscilloscope. Things you can notice are these downward going sync pulses. These denote the start of each scan line of video. So after the sync pulses, this part of the active video signal, the higher up the signal, the brighter the picture is. So if you look, if I increase the lighting, for one thing it gets washed out, and you can see that those fringes get higher. But you also may have noticed that the entire waveform shifted up and down. And that's because video signals are AC coupled. So the actual DC level doesn't matter, like if we move the signal up or down. What your TV looks at is how far above the sync pulses it is. So this will come in handy when I explain the circuit now. Okay, so here's the entire schematic again. I'd actually like to start by first looking at the actual jacks on the device. So you can see here where I've drawn this. If you look at the audio side of things, you can see that the input jacks are directly connected to the output jacks. So left in goes to all three outputs, and the right in goes to all three outputs for the right channel. The only thing interesting here is that that the right input jack has a built-in switch, so that if you don't have a right channel plugged in, it will duplicate the single channel of a mono device onto both output channels. Now on the video side, the video input goes to an amplifier, and the output of the amplifier goes to all three of the jacks. Now, what I didn't mention earlier is the reason there needs to be an amplifier on the video is because video devices are expected to have a 75 ohm termination resistance. If you have three devices connected on the output and each has a 75 ohm resistance, you end up with an equivalent total resistance of 25 ohms, which can drag down the output of your video generating device and lead to a distorted picture if it's not made to, if it's not expecting to drive additional loads. And there's also an issue of the cable impedance, which is a topic I don't understand too much. Basically, if you have a 75 ohm cable, it needs to have a 75 ohm resistance at the end, or else you'll get strange signal reflections when you deal with high frequency signals such as video. So that's why you need an amplifier on the video side. And since audio is much less sensitive, like these RCA jacks for audio aren't impedance sensitive, then you can just parallel them and it works fine. So now move up to look at the rest of the actual schematic. Let's start now with the power supply of the circuit. The 120 volts coming in goes directly into this transformer, which outputs around 12 volts AC. Then it goes through a 68 ohm resistor, which limits inrush current and prevents quick changes in voltage. Then we have a puny single diode rectifier, which is a 1N4002, I believe. Simple 1 amp diode with a 1 nanofarad capacitor across it for noise suppression purposes. I would have preferred to see a full bridge rectifier, but this still works. So then the rectified AC signal, it feeds into some filter capacitors. You have a large 1000 microfarad capacitor. That's this one on the board. We have a 100 nanofarad capacitor for decoupling. And we have another 100 microfarad capacitor for more power supply smoothing. And then we have a red LED and a 2.4K resistor, just as an indicator so you know that it's on. And this supply generates about 10 volts DC. Now let's look and see what that feeds. The 10 volt supply feeds this circuitry here, which is these components. So we have 10 volts goes into a 330 ohm current limiting resistor, which leads to a 4.3 volt Zener diode. So this is a simple shunt regulator which basically means we end up with 4.3 volts on this wire here. And then we have a 10 microfarad capacitor to provide some extra bulk capacitance for higher current pulses. And we have some more decoupling capacitors. Now, what this 4.3 volts gets used for is where the interesting stuff happens. Now we get to the part of the circuitry where the actual video comes into the unit. And as I said earlier, devices have a 75 ohm resistance on video inputs. So we have that here as this resistor, which I believe is that resistor on the board, right next to the video input jack. And now we have this basically a clamping circuit. When there's one of those negative going sync pulses on the video input, it reaches a low point. Then we have a simple clamping circuit here. So what happens is, so when that's low, you have 4.3 volts here. So this diode charges that capacitor a bit. And then this line ends up being about 3.7 volts, which is 4.3 volts minus a diode drop of about 0.6 volts. And as I mentioned earlier, video signals are AC coupled, so the actual voltage itself doesn't matter, it's only the changes in voltage. And that's why it's okay to run the video through a capacitor. It shifts the voltage up, so the low pulses in the video, once it gets here, are at about 3.7 volts. And then the higher parts of the signal are still that much higher, as they should be. Then once we have that elevated signal, it goes through this little transistor, which is this one on the board, in an emitter-follower configuration, which basically means the emitter is always about 0.6 volts below the base as it pushes current in to maintain that value. And that feeds another emitter follower in like a Darlington pair. Basically, when the video signal goes up, this line goes up by the same voltage, and this line goes up by the same voltage, and this line goes up by the same voltage. And then this gets fed through a capacitor, which like we said is okay, and then the video out pin goes up by the same voltage as well. Now, you notice there are also some resistors here I didn't talk about. These resistors on the collectors of the transistors, I guess they're just there to provide some current limiting to prevent excessive current from going into the transistors. And it also evens out some of the thermal dissipation, so not all of the heat goes into the transistors. Although this larger final transistor does get rather warm. Now, we also have these emitter resistors, and that's just to bring down the voltage when the input goes down, because the transistors can only increase the voltage, they can't decrease it. So this resistor provides the compensating part, and as well with the output. And then that's the entire circuit. Video goes in, it gets raised, so its lowest point is 3.7 volts. Then it gets buffered by these emitter followers. So then at this point, the lowest dips of the signal are about 2 more diode drops down, so around, it's about 2.5 volts when the video is at its low point. Then, when the video signal goes up a volt, then this point should be 3.5 volts. So that's the circuit. Now, you can put it back together. So there you are, folks. That's what's inside a video splitter. Hopefully you learned something today. If you liked this video, be sure to like, subscribe, comment, and share. This has been eDoc2020, and I'll see you in my next video. Goodbye.